So hello everyone again. This is lecture 3 part 3 of dual nature of radiation and matter. Let's start with the further discussions in which we held in the previous lecture. So I was trying to summarize all the portions of the wave particle of photon. So let's start that discussion directly only. So I am Sameer Lavankar. Let's begin our discussion. So right now we are on the 7th part, that is the particle nature of light, that is the photon. In previous discussion we already completed the introduction part, electron emission part, photoelectric effect, experimental study of photoelectric effect and wave theory of light, and the previous discussion we completed with the Einstein's photoelectric equation, that is energy quantum of radiation. Okay. So let's start with particle nature of light, that is photon. Okay, so let's summarize the photon picture of electromagnetic radiation as follows. Okay, the first thing says that in interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. So these are all the basic ideas, of these are basically ideologies which we try to understand, or which we try to make so that we can understand the photoelectric effect. Okay, so first of all thing is that this radiation we are understanding it as, let's say these are the discrete particles which are being called as photons. Okay. Each photon has an energy E. I already explained this in the previous discussion only. So basically this has energy E which is equal to h nu and momentum p. Please remember momentum is denoted by p value here, that is equal to h nu upon c. What is c here? C is basically the speed of light. C is basically the speed of light. Okay, next thing is all photons of light of a particular frequency nu or wavelength lambda have the same energy E, which is equal to h nu upon lambda. Okay, so you can just understand this directly only. So we are just trying to say we are just changing nu into lambda value here. Okay, so nu is equal to c by lambda. So all photons of light of a particular frequency nu or wavelength lambda have the same energy, quite evident because every particle we are just, this is just all the summarization of the assumptions, summarization of the ideas which we are understanding for a photon. Okay. So all photons of light of a particular frequency nu or wavelength lambda have the same energy E, which is equal to h nu, which is equal to h c by lambda. So we can just write this as also equal to h c by lambda, and momentum p which is equal to h nu by c, which is also called as h nu by lambda. Okay, so this can also be written as h by lambda. Okay, whatever the intensity of radiation, so this is nothing but speed is equal to distance upon time only, nothing major typical here. Whatever the intensity of radiation may be, by increasing the intensity of light of a given wavelength, there is only an increase in the number of photons per second crossing a given area, with each photon having the same energy. Okay. So just again theoretical part is being explained, experimental part is being explained here. So if we try to increase the intensity, what is happening is increase the number of photons per second crossing a given area. Basically the value of n upon a into t is being increased, right, with each photon having the same energy. Thus photon energy is independent of intensity of radiation. So this energy, this h nu value is independent of the intensity of radiation, that is being only explained here. So right now we are just circling around these 3-4 points only, nu value, independent of intensity, etc. Only the things to be conceptualized, these are being varied upon. Okay. Next thing is photons are electrically neutral and are not deflected by electric and magnetic fields. This is a very important point, that these are electrically neutral people. So they does not have any charge and are not deflected by electrical and magnetic fields. Okay. In a photon particle collision, such as photon electron collision, let us say this particle is electron here, the total energy and total momentum are conserved, that is there is a complete dissipation of energy, but that energy is not, let us say, added up, let us say not leaked up, the complete energy and momentum are conserved. So basically you can even use the conservation energy equation there and conservation momentum equation also there. Okay. However, the number of photons may not be conserved in a collision. Okay, please remember this. The number of photons may not be conserved, but the energy and the momentum equation will be conserved, or basically energy and momentum will be conserved. The photon may be absorbed or a new photon may be created. Okay, so these are the basic summarization points which you need to remember for photon. Okay, so let's stop the complete discussion now and let's move on with some of the examples which we need to, which is very important for our as far as exams are considered. Okay, very easy, you just need to remember, because there are not even different formulas only, there is something called as h nu, h c by lambda, then k max is equal to h nu minus phi naught. So, very small equation, you just need to understand how to apply those formulas, and you just need to remember the values of, let us say, h etc., h c etc. Okay. So, let us go on, let us read the question first. So, monochromatic light of frequency 6 into 10 to the power 14 hertz. So, basically let me just keep on writing here everything. So, new value is given to you as 6 into 10 to the power 14 hertz. Fine, the power emitted is equal to this. So, power is also given to. So, basically some use of power is being used here. Okay. So, power basically will be related to some sort of intensity portion also. So, let us go on, let us just see here what is being asked. So, this is 2 into 10 to the power minus 3 watts. Okay. Question first asks, what is the energy of a photon in the light beam? Okay. As we know that the photon has an energy which is equal to h nu. As the value is nu directly given to us, you can write A is equal to energy which is equal to h nu. What is the value of nu? Nu is already given to you in the question. What is the value of h? Please remember the value of h, which is equal to 6.63 into 10 to the power minus 34 joule seconds. Fine. So, just putting the value, the multiplication is already being done here. So, this is just, I am just leaving the mathematical formulation. So, the final energy which you will get for the single photon is equal to 3.98 into 10 to the power minus 19 joules. Okay. Next thing is second question, that how many photons per second on an average are emitted by the source. Okay. So, quite evident, as you can see here, what we know, that power can be related to the number of energy as equal to n into. So, what is basically happening here? So, one, we know the value of energy being radiated or being radiated by a single photon. That single photon, when it get bulked up, will give some amount of power. That power is basically given to you in the question. So, what we can do, we can just multiply which value, this E value. So, E value can be multiplied with this value n, which will give you the value of power. You know the value of the power, right? So, that in that way we can find out the value of n, which is equal to P by E. I guess the concept has been clear. Okay. Because this is the energy of one single photon, we are trying to find out the number of photons. So, when this complete energy gets added up, then we will get the complete power being emitted by the this light. Okay. So, if n is the number of photons emitted by the force per second, the power P transmitted in the beam equals n times the energy per photon, quite evident. So, that P is equal to n into E. N into E, basically n multiplied by a single energy photon will give you the complete power, total power. Then n is equal to P by E. P value is given to you as 2 into 10 to the power minus 3 watts, and similarly the value of E is given to you as 3.9 into 10 to the power minus 19 joules. Okay. Watt per joules give you photons per second. Okay. Let us move on to the second example. I guess this example is based on your photoelectric equation only. So, let us go very slowly. So, question given is the work function of cesium is 2.14 electron volts. Okay. So, the value of phi naught is given to you in the question as 2.14 electron volts. Fine. Question first asks is, what is the threshold frequency for cesium? Okay. So, in the previous lectures, in the previous discussion, we already heard that the frequency, that is nu naught, is nothing but equal to phi naught divided by the value which is of Planck's constant. So, this is the equation, just everything is given to you, that is 2.14 upon what is the value of h, that is 6.63 into 10 to the power minus 34 joule second, right. This is in electron volts. Okay. Please remember, when you divide electron volts by this value of joule second, finally the answer which you need to understand will be in terms of hertz. Okay. So, basically just calculate the electron volt is basically a charge. So, 1.9 into 10 to the power minus 19 coulombs, and then using that complete concept, finally you will get the answer of frequency which is equal to 5.16 into 10 to the power 14 hertz. Okay. So, you cannot just directly multiply these values and get the value directly equal to this. Please change this electron volt equation, which you know this is basically a charge of an electron only, and then just multiplying it by that value you can get the answer. Okay. So, basically the first question is that the threshold frequency to be known, and threshold frequency is nothing but nu naught, which is equal to phi naught by h. Okay. Please remember, please convert this electron volts into by multiplying the charge of an electron, which is equal to 1.9 10 to the power minus 19 coulombs. Okay. So, this thing has been done. Let us move on to this decision now. So, thus for frequency less than this threshold frequency, no photoelectrons are ejected. Okay. Second question says that the wavelength of the incident light, if the photocurrent is brought to 0 by stopping potential of 0.6 volts. Okay. So basically now they are trying to, what they are trying to find out, they are trying to find out that wavelength, or let us say that frequency, if we go in similar terms, that frequency at which the stopping potential is happening of 0.60 volts. As we know that stopping potential is different for different frequencies, so we are just trying to find out that value. Okay. So how to do that mathematically? We have only one equation, that is photoelectric equation. So just try to write everything. So let me just write everything here only. So basically we know that E V naught, this V naught is basically the potential, this stopping potential, right, which is equal to nothing but H nu minus phi naught, right. You know the value of phi naught, which is equal to nothing but 2.14 electron volts, right. You know the value of Planck's constant, you know the value of nu you can calculate equal to C by lambda, right. So it is equal to C by lambda, right. So you know this value, you know the value of E also, so you can directly calculate the value of V naught. So only that thing. So basic crux is you just need to remember this equation. You know the value of nu naught, you know the value of this E, you know the value of H, you know the value of C, that is 3 into 10 to the power 8 meter per second, you know the value of phi naught, you just need to calculate the value of lambda. Fine, everything is given, just mathematically formulate it and you get the answer. So photocurrent reduces to 0 when maximum kinetic energy of the emitted photoelectrons equals the potential energy EV naught by the retarding potential V naught. Einstein's photoelectric equation is, so that thing is already written here, or so they just change this. I will try to understand, make you understand what is happening here. So basically what they did is, so they just rearrange the terms and you got the equation as lambda is equal to Hc upon EV naught plus phi naught. Okay. So just put the terms, you know the value of H, that is 6.63 into 10 to the power minus 34 joule second, you know the value of C, that is 3 into 10 to the power 8 meter per second, you know the value of EV naught given to you 0.6 electron volts, it is given here, right. So E is basically you are just multiplying it with a charge value here. So you get, if I divide this equation by E, then you can get the same equation in terms of electron volts, right, because E has the value equal to your electron charge. Okay. And phi naught is nothing but 2.14 electron volts, fine. So basically after mathematical calculation, the lambda value is equal to 454 nanometers. Okay. Please look out to the calculation once, please try to do the calculation once, because sometimes people may do mistakes here and then marks can be deducted. So please try to at least do once this complete calculation, very easy. So just try to do, and then finally you can get the answer equal to lambda, which is equal to 454 nanometers. Okay. Let us go on with the next discussion. Okay, again simple questions, only the frequency is being varied. So we are just trying to find out what happens when the yellow color is visible, green color is visible, etc. Okay, equation is again based on photoelectric effect only. So please look out to the question now. So the example says that the wavelength of light in the visible region is about 390 nanometers for violet color, about 550 nanometers for yellow color, and about 760 nanometers for red color. Fine. What are the energies of photons in electron volts at the violet and average wavelength of yellow green color and red end of the visible spectrum? The value of E is also given to you, and the value of electron volt is also given to you, that is 1.6 into 10 to the power minus 19 joules, and the value of H is also given to you, that is 6.63 into 10 to the power minus 34 joules second. Fine. Everything is given, you need to find the energy. So what is energy? Energy, we know energy is equal to H nu, right. The value of wavelength is given to you, so you can just change it equal to Hc by lambda, right. H is given to you, C is known to you, and lambda is given in the question. So nothing typical, you just need to find out, you just need to put the values here and then you can get the answers, right. So value for first is 3.19 electron volts. Please try to calculate it, please try to mathematically calculate it itself, so that you can understand what is actually happening here, right. It is 550 nanometers for the second point, that is 2.26 electron volts, and it is third for 760 nanometers. Everything is written, you just need to mathematically calculate it. E1 is equal to 1.64 electron volt, at for lambda 1 is equal to 760 nanometers. Okay. Next is for a photoelectric device to operate. Let us read the second question now. From which of the photosensitive materials with work functions listed in table and using the results of 1, 2, 3 of A, can you build a photoelectric device that operates with visible light? Okay. So, for a photoelectric device to operate, we require incident energy light E to be equal to or greater than the work function of the material, right. Now, thus with the photoelectric devices will operate with violet light, photosensitive material sodium, potassium and cesium, right. So, they are just trying to understand. So, basically the table which was given in the initial part of the question, and when I try to understand, make you understand the photoelectric equation, let me just go there once. So, basically this table is being explained there. So, basically using this work function values, can we try to understand that which of these metals can be visible or can be used as a photoelectric device. Okay. So, just try to look out to this table and try to understand from that sequences there. Okay. So, basically we can find out that this device will operate with violet light, photosensitive material is sodium, because sodium will have a work potential of 2.75, potassium has a 2.3 and cesium has 2.14, right. So, basically sodium, potassium and cesium can work with this violet light. Okay. For this yellow green light, cesium can only operate, and for red light any of these photosensitive materials cannot be operated. Okay. So, this is the basic crux of this second part. Okay. This is how the application of this photoelectric effect can be come into basic our surrounding pictures. Okay. Let us start the final concept, that is wave nature of matter, and then we can go on to the division and German experiment. Okay. So, let us start the wave nature of matter. The complete concept before that is already completed, very detailed. Let us start with the wave nature of matter. So, in this we will try to understand what is basically happening of the photon. So, can we actually find out the value of E, let us say mass, nu, etc. of this simultaneously or not? We will try to understand that complete concept here. Okay. So, the wave nature of light shows up in the phenomena of interference, diffraction, polarization. These all things have been clearly explained in the wave optics chapter. You can go and refer them directly. So, why was basically there is a need to understand this complete concept of wave particle theory, so as to understand, so as to make you understand these all the concepts, interference, diffraction, polarization, etc. If let us say in a hypothetical sequence that these sequences are being not observed, then the complete major part of the light sequence can be absorbed or can be explained using the Descartes theory or particle theory of light. But because of these phenomena being observed by light, we need to you need to take the help of wave nature theory and understand these concepts. Okay. So, the wave nature of light shows up in the phenomena of interference, diffraction and polarization. On the other hand, in photoelectric effect and Compton effect, which involves energy and momentum transfer, radiation behaves as if it is made up of a bunch of particles or the photons, right. So, only they are just trying to say that this complete effect of photoelectric effect has been observed, has been explained using the complete photons concept only. Okay. So, let me stop it here only. I will try to again revise or again start the wave nature of matter in the next class discussion only. So, let me conclude it here. So, the course progress for you, we started with the introduction part, then electron emission, basically how are these electrons being emitted from the metal surface, then the complete concept of photoelectric effect, what were the Hertz observations, what were the different observations by different scientists, which will be explained in this third point. Then experimental study as in changing the intensity, changing the frequency, what has an effect on the photoelectric effect. Then the photoelectric effect and wave theory of light, as in how the wave theory could not explain the basic concepts of photoelectric effect was being explained here. Then the Einstein's photoelectric equation, everything which was been explained in the previous discussion of photoelectric effect, experimental analysis of photoelectric effect, the the parametric studies of intensity variation, frequency variation were being explained using Einstein's photoelectric equation. Finally, in the previous discussion, we concluded the particle nature of light, the photon, some experiments, some examples were being explained to you. 3 examples were being explained to you, and finally, in the next lecture, we will start with the wave nature of matter, and then division and German experiment only remains, and that will be the end of this complete lecture. Okay. So, let me stop it here only. So, thank you so much.